Let's continue doing the factor groups for some more problems and results. Uh, our first result that we are going to do today is that if n is a normal subgroup of G and phi is a homomorphism from G to G prime, then phi of n is normal phi of n is normal in phi of G, and if n prime is a normal subgroup of G prime, then phi inverse of n prime is normal in G. So let us try the first one. So phi is a homomorphism from G to G prime, and n is a normal subgroup. And that implies G n G inverse belongs to n for all G in G and n in n. And that is a necessary and sufficient condition for a subgroup to be normal. So what we need to do is we'll take corresponding elements from G prime. So let n prime belongs to phi of n and G prime belongs to phi of G. So this implies phi of n is equal to n prime and phi of G is equal to G prime for some n in n and G in G. So, but given that n is a normal subgroup, so n G and G inverse belongs to n because n is normal, and that implies phi of G and G inverse belongs to phi of n, and that implies phi of G times phi of n times phi of G inverse belongs to phi of n. And that implies this is G prime, this is n prime, and this is G prime inverse belongs to phi of n, and that implies phi of n is a normal subgroup of phi of G, not G prime. So the next one is n prime is a normal subgroup of G prime implies n prime dot G prime n prime G prime inverse belongs to n prime for all n prime belongs to n prime and g prime belongs to g prime. So what we do is, similarly what we'll do is let n belongs to phi inverse of n prime and g belongs to g. So this implies phi of n is equal to n prime and phi of g is equal to g prime for some n prime belongs to n prime and g prime belongs to g prime. And that implies phi inverse of that implies n prime, sorry, g prime dot m prime dot g prime inverse belongs to n prime, implies phi inverse of g prime n prime g inverse belongs to phi inverse of n prime. And that implies phi inverse of g prime dot phi inverse of n prime dot phi inverse of g prime inverse belongs to phi inverse of n prime. And that implies g times n prime times g inverse belongs to phi inverse of n, implies phi inverse of n is a normal subgroup of G. Now let us define a special normal subgroup. A normal subgroup H of G, or we'll say M of G, M of G is maximal if there exists there are no normal subgroups n of G such that M is a proper subgroup of n, which is a proper subgroup of G. Meaning there is no subgroup, normal subgroup containing M. That implies there are no proper normal subgroup of G properly containing M. We have a very beautiful necessary and sufficient condition for a maximal subgroup. Now let us derive a necessary and sufficient condition for a normal subgroup to be maximal. So the theorem is this. A normal subgroup M of G is maximal if and only if G over M is simple. So this is the two-part proof. So let us assume that let M be a maximal normal subgroup of G, and assume that G over M is not simple. So when GM is not simple, then there exists, let us say, M plus A. There exists a normal subgroup, or exists a normal subgroup, let's say K, normal proper subgroup K of G over M. That is, K is strictly a subgroup, is normal and strictly a subgroup of M. And it is not, it is actually this is identity subgroup of G over M. That's also a proper subgroup of K, which is a proper normal subgroup of G over M. Now let us consider the canonical homomorphism gamma from G to G over M. So that implies gamma inverse of K is a normal proper subgroup of G, and it's also non-trivial because M is the G over M is the it's an onto map. So this is the inverse of G over M is the trivial subgroup of G, and gamma inverse of M is the whole of G. So this lies in between these two. So now that implies and also that implies gamma inverse of K contains M because of this relation. That implies M is not a maximal normal subgroup. Y inverse of K is a normal subgroup of G containing M, which is not possible because M is already a maximal normal subgroup. Now let us assume let G over M is simple. Consider same homomorphism G to G over M, gamma is onto. Assume that M is not maximal. That implies there exists a normal subgroup K of G such that M is a proper subgroup of K, is a proper subgroup of G. So this implies gamma of M this implies that gamma of K is a non-trivial proper normal subgroup of G over M. G over M means actually you should say gamma of G, and which is already equal to G over M because it's onto. This is non-trivial because it's a proper subgroup of G. Proper normal subgroup because K is M is a proper subgroup of K. And K is normal. So a homomorphism preserves normalcy because that's what we proved earlier. So gamma of K is a non-trivial proper normal subgroup of gamma of G, which is already in Gm, which implies G over M is not simple, and that's a contradiction, and that implies M is maximal. We are using the same tool to prove necessary and sufficient condition. Now we are going to define two special subgroup normally very useful in non-abelian groups. For abelian groups, these two subgroups are trivial subgroups, trivial subgroups. Yeah. So the first one is the center of a group. Center of a group. It's all normally denoted as C of. So the definition goes like this. Let G be a group and C of G is equal to all elements from G such that it commutes with all elements of First we need to prove that this is a subgroup. Then we call that one as, actually it is a normal subgroup. Actually it's an abelian subgroup. So first thing is, what we need to prove is C of G is an abelian subgroup. Okay. So what we need to prove is closed. We have to prove that it's C of G is closed. That is because that states Z1, Z2 belongs to C of G implies Z1 Z2 G is equal to Z1 G Z2 equal to G Z1, Z2 imply Z1, Z2 belong to Z of G. And that is a condition for Z of G. Identity of G belongs to Z of G because EG is equal to GE for all G in G. Inverse of an element Z in G belongs to Z of G because Z inverse of G is equal to G inverse, because if you take G on the other side, this G inverse on this side and this G inverse on the other side, we'll say G equal to GC because C belongs to C. So it is closed, identity belongs to this and inverse also belongs to this. So C of G is a subgroup of G. Now we need to prove that it is abelian. What we need to prove is Z1, Z2 belongs to C of G. So Z1 comma Z2 belongs to G. That implies it is actually trivial because Z1 Z2 is equal to Z2 Z1. Here what you are using is Z2 belongs to Z of G, which is a subgroup of G. So we are replacing Z2 with G, and that matches with the condition of G. So with this condition, this is definitely an abelian group. This implies C of G is abelian. So before coming to the next special subgroup of a group, we need to define a couple more things. Definition. Let G be any group and S is a subset of G. And let us assume that S is equal to GIs for some I belongs to some index set I. It could be infinite or finite. Then the smallest subgroup of G containing S is called the subgroup of G generated by S and is denoted by S. So there is a small theorem here or result. or we want to define one more term here. If S is finite, then the subgroup generated by S is called a subgroup is called finitely generated. It's called finitely generated. That does not mean that the subgroup is finite, but the only thing is it is finitely generated. Now, if there exists a subset S Gi, I belongs to I, such that G is generated by S, then the group itself, the group G is finitely generated. This is actually a subgroup, but if the whole G is generated by a subset, then the whole group is finitely generated. Now, every element of a subgroup of G generated by a subset S of G, this is a subset, is a finite product of powers of elements from S. So this is a very simple proof. Let K be the set of all finite product of powers of element from S. See, it is the smallest subgroup of G containing S. So, here we are taking the finite product of powers of elements, means this set of all, this kind of collection is a subset of the generated subgroup. That implies K is a subset of the subgroup generated by S. Because this is actually the subgroup containing all of S, meaning every finite product of finite powers also belongs to this. So that means this. Now we need to prove that K is a subgroup. If we prove that K is a subgroup, then K is equal to this, because this is the smallest subgroup. So now K is a subgroup. That is clear because K is closed. K is closed? Because you need to say product of integral powers of element. So K is closed because if you take two elements from here, the product of two elements will be again a finite product of integral powers of element. So K is closed. K contains the identity. Why? Because E is equal to A times A inverse. So this is a finite product of integral powers of an element from A, where A belongs to S. And K contains the inverse of all elements of K. Why? Because you let A is equal to A1 R1, A2 R2 dash dash AN Rn belongs to K. And this implies that An minus R1n, A2, An minus 1 minus Rn minus 1 dash 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 A1 minus R1 also belongs to K, because this is a finite product of integral powers of elements from S. And this is nothing but the inverse of this. If you multiply these two together, you get the identity. So that means A inverse also belongs to K. So K is a subgroup containing all finite products of the integral powers of elements from S. So that means, but the subgroup generated by A is the smallest subgroup. So they are equal. And that implies K is equal to S. K is equal to the subgroup generated by S. So the subgroup generated by S contains all the finite product of integral powers of elements from S. Now, our next attempt is to define another special subgroup, basically used for non-abelian groups. The center of a group, okay, see, what does this mean? This means a subgroup of G that commutes every element of see, if G is abelian, then the center of G is equal to G. There is no other element other than the elements from this subgroup that commutes with all elements of G, because G is already an abelian. That is why the center of group is more useful when G is non-abelian. If it's an abelian, it is the same. Our next attempt is, if there is an abelian, non-abelian group G, Our aim is to find another group, another abelian group where we can define a homomorphism from G to that group. For example, we are going to construct a group G dash which is an abelian group, and this group, the group is in such a way that we can define a homomorphism G to J such that even if this is a non-abelian group, we are making this as an abelian group, meaning phi of AB in G is equal to A of phi of A times, gamma of AB is equal to gamma of A, gamma of B, and these two elements are in the target group, and it is an abelian group, so we can write it as gamma of B times gamma of A, and that is gamma of BA. So we are actually abelianizing this group. Even if it's a non-abelian group, we are making a abelian group and then homomorphism so that you can abelianize the non-abelian group. That is the plan. The way we are going to do is, this will be a factor group of G. Meaning, you are going to find a subgroup of G such that G over M is abelian. Okay? So, suppose you want to commute every element of G prime. What is the condition there? So, AB is equal to BA for all A, let us take it as A, B in G prime. This is how the abelian group works. And what does this mean? This means that AB, then you take B here, or you take A here, A inverse is equal to B. And that implies AB, A inverse, B inverse equal to E of G prime. So if this condition is true in here, then G prime is abelian. So this is a relation that we can define on a subgroup of G. See, what is the definition of coset? If H is a subgroup of G, G over H is the left or right cosets of H, and which is defined as A is related to B if A inverse B belongs to H. So there is a relation here, and that is the kind of relation you are getting here. So if A, B, A inverse, B inverse if is equal to E for some A comma B in G, collect those elements from G and form a subgroup. And these elements are called commutator. So, we are going to collect elements from G to form a subgroup of G, and that will become a normal subgroup of G, and so that you can define a factor group. And that factor group will be an abelian group. And that is the plan. So, definition. Let G be a group for A comma B belongs to G, then A inverse B inverse is called a commutator. The subgroup generated by all commutators is normal in G and is called the commutator group. Commutator subgroup of G. And this is actually and is denoted by C. Normally the commutator group is denoted by C. We don't need to show that it is a subgroup because we already defined the collection as a subgroup generated by all commutators. Any element, any group of elements from any set of elements from here can generate a subgroup of G. We already seen that. Now what we need to prove that it is what we need to prove is that C is a normal subgroup. So for that what we need to do is let C inverse D inverse belongs to C. This is how an element of C looks like, or the product of this. And G belongs to G. What we need to prove is G times C inverse, D inverse, G inverse, or you can say here, you can inverse here, and you can say G here, belongs to C. So we need to calculate this. So what we do is G inverse CD, C inverse D inverse G equals G inverse CD, C inverse. In between these two, I am going to insert E, D inverse G. We can do that, right? Now we are going to replace this E with G inverse C, D, C inverse. I'm going to write here G inverse and G. This I'm going to write it as G, D inverse, D, G inverse. This is E. So this is the total the product of 4 elements will be E. And that is this. Now this is actually G inverse C, these two, and D, this one, I'm going to write it as G inverse C inverse, G C inverse or this can be written as G inverse C inverse. See, if you expand this one, this will be C inverse G inverse of inverse, and that is these two together. Okay. And after that you have a D inverse here. Then what we have is D G inverse then you have E times G D inverse, sorry, we'll write it as DG inverse times E inverse. And this actually belongs to C, and this also belongs to C. And that implies the whole element belongs to C. And that implies C is normal. So the idea of constructing the commutator subgroup is to abelianize a non-abelian group. So if G is a group, any group, and C is the commutator subgroup of G, then G over C has to be an abelian. Then only our effort of building this subgroup is meaningful. So then G of C, the factor group G over C is abelian. Then only we can construct a map from G to G over C such that you can make the elements of G as an abelian group. So another result is, let C be the commutator subgroup of G. Then G over C is abelian. We need to prove that. So how do we prove? We need to show that for all A comma B in G, AC times BC is equal to BC times AC. These are the elements from the factor group G over C. So we'll start with this. AC times BC is equal to AB times C. So here what we do is, see what is in C? C contains all the elements of the form A, B, A inverse, B inverse, or its products. So if an element is in here, then A, B, A inverse, B inverse, C is equal to C, because it's already here. And that is the result we are going to use here. So what we do is, this is equal to AB. We are going to multiply an element from C, that is B inverse, A inverse, B, A, C. This is actually an element of C. So, A, B, C is equal to this. And this is nothing but, if you compute this one, this is E, A inverse, B, A, C. And if you compute these together, you get E, so it will be B, A, C. And that is equal to B, C times A, C. So, G over C is always abelian. Now our next question is, how close is this commutator group when you abelianize a group? So what we have seen so far is G is any group, C is a commutator group, and C is a normal subgroup of G. So we can define G over C. So this is a normal subgroup of G. Okay, and we found that this is abelian, which does not say that there is no other subgroup other than C, which makes the same condition. So if we take another normal subgroup N of G such that G of N is abelian. So this N doesn't need to be a normal commutator subgroup. So what is the relation between if you take any subgroup and a commutator normal subgroup? The result says that G by N is abelian if and only if C is N contains C. Meaning G over C is the largest abelian factor group in G. So that is our next result. So let C be the commutator subgroup of G and N be another normal subgroup of G. Then G over N is abelian if and only if N contains C. So that is our next theorem. So let us assume that G over N is abelian. We need to show that commutator group is a subgroup of N. That implies An times Bn is equal to Bn times An. And that implies Abn is equal to Ban. And that implies A inverse B inverse belongs to N. And this is in C, and this implies C's. These are the elements from C, and that is in the normal subgroup. So C is a subgroup of N. Now we need to show that if C is a subgroup of N, then G over N is abelian. So let C is a subgroup of N. We need to show that A times N times B times N is equal to B times N. And this is what? This is actually A, B, N. So this is actually equal to, now what we are going to do is, we are going to insert an element from C here. So AB, B inverse, A inverse, B, A, this is actually an element of C. And C is in N. So if you take any element from N and multiply it with this, it doesn't make any difference here of N. And this is actually equal to B inverse cancel, A inverse cancel, that is equal to B. And that is equal to Bn times A. And that implies G over N is. So if there exists another normal subgroup of G such that G over N is an abelian, then N should contain the commutator group.